Hello, geometry students. I hope you are doing well. We are now in section 7-4, and we're still talking about similarity. And today we are going to be specifically talking about similarity in right triangles. What I'd like for you to be able to do by the end of this lesson is to use relationships in similar triangles to find missing values and set up proportions, things like that. So to begin with, we have a definition of geometric mean of two numbers. So what is that? A geometric mean is essentially a particular value in a proportion where one of the cross products is the same. So I'm just going to write this out kind of algebraically so you can see what that is. So let's say that we have A and B, and if we have A over X is equal to X over B, then this X right here, this X squared, would be that geometric mean. So essentially, the X is the geometric mean. So when the bottom of the first ratio is equal to the top of the second ratio, that is the geometric mean. Let's use that information to calculate geometric mean between two numbers. So in example 1, we want to find the geometric mean between 4 and 25. So, and it does say to simplify to simplest radical form. We're going to skip that just for today because I want to cover that type of stuff in a different lesson. So we have 4 and 25. I'm going to put 4 over X is equal to X over 25. Now I cross multiply and I have X squared is equal to 100. Square root both sides and I get X is equal to 10. So my first geometric mean is X is equal to 10. Okay, for my second geometric mean, I'm going to do that again. I have 5 over X is equal to X over 30. Cross multiply, and we get X squared is equal to 150. Now we're going to square root both sides. And when we do that, we get approximately 12.3. So these were just some quick examples, and that's as complex as geometric mean is going to get for this class. Next, we have something about right triangles. So it says the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. Essentially, what this is saying is this. We have a big right triangle. And remember, an altitude connects a vertex to the opposite side perpendicularly. So I'll just remind you of that again. Altitude is perpendicular to opposite side. So in this image right here, I have the biggest triangle, and it is going to be similar to both this smallest triangle and this medium-sized triangle. So we're going to use that information to set up similarity statements. So in example 2, we want to write a similarity statement for the three triangles. First, I want us to identify what is the small leg, the long leg, and the hypotenuse of each triangle. And one strategy that we can use, and the strategy that I encourage you to use, is to redraw this. So, we don't have our 90-degree angles in here, but this is meant to have that, like so. So I have three triangles. I have this small one, I have this medium-sized one, and then the very biggest one. I'm going to draw all three of them. Instead of being all in one image, I'm going to separate them. So I have the smallest triangle, and that is ADB. So I'm going to label that ADB. Then I have the medium triangle, so I'm going to draw that next, just a little bit bigger. Excuse me. Excuse me again. So the medium triangle is BDC. And the largest triangle is ABC. Now that I have my images separated out and all drawn in the same orientation, it's easier for me to directly line up how these triangles are going to correspond. So let's write in the short leg for the small, medium, and large triangle. The short leg for the small is segment AD. Short leg for the medium triangle is BD. And the short leg for the large is AB. The long leg for the small is DB. The long leg for the medium is DC. And the long leg for the largest one is BC. Finally, we're going to do the hypotenuse. So the hypotenuse of the smallest triangle is AB. The hypotenuse of the medium triangle is BC. And the hypotenuse of the largest triangle is AC. Alrighty. Now that we have that all lined up, I'd like to also write a similarity statement. For our similarity statement, we are going to say triangle ADB is similar to triangle BDC, which is similar to triangle ABC. And there we have that example all done. Let's flip our page over and work on the back problems. On the back problems, we are going to use the information that we know about these similar triangles in order to solve for missing values. And if we have any decimals, then we're going to just round to the nearest tenth. What I want to do first is to separate these triangles out as small, medium, and large, and to label them again. So my smallest triangle, and I just tend to like this orientation. If you have a different one that you prefer, then you can do that. Let's make sure that I'm double checking myself. Yeah, okay. I was thinking about something and I wanted to double check my work real fast. Okay, so this is my small triangle, and then my medium triangle is going to have short leg 6, long leg 9, hypotenuse Z. And my largest triangle is going to be Y, Z, X, and 9. Okay. When I do this, something that I suggest is if you can use the Pythagorean theorem, then do it, because that's one of the easiest things to use. So what I want you to notice in this medium triangle right here, I can easily find z by using the Pythagorean theorem. So let's do that. I'm going to have 6 squared plus 9 squared is equal to z squared. So that's 36 plus 81 equals z squared. 36 and 81 is going to equal 117. Square root both sides. And we are going to get about 10.8. So 10.8 is equal to z. So I'm going to plug that in right here. Now that I have 3 known sides of this triangle, I can easily set up proportions for all the others. So I have x and y in that top small triangle. I can say the x corresponds with the 6, and this 9 corresponds with this 6. And that's how I can calculate the x value. So let's do that. I'm going to put x over 6 is equal to 6 over 9. Cross multiply. So I've got 36 is equal to 9x. Divide by 9. X is equal to 4. Alrighty, x is equal to 4 here. So we can easily use the Pythagorean theorem to find what y is, or we can set up another proportion. I'll set up one more proportion with you just so you can see what that would... Actually, no, I don't want to set up a proportion just because of this 10.8 here, and it was rounded, so I think that'll make it messier. So let's go ahead and use Pythagorean theorem to find that last side. So I'm going to say 4 squared plus 6 squared is equal to y squared. That's 16 plus 36 equals y squared. 16 plus 36 is equal to 52. Square root both sides, and I'm going to get y is equal to 7.2. So what I want you to notice, what I did here is I used whatever strategy was going to get me to the answer in the simplest way. So sometimes I used proportions, and sometimes I used the Pythagorean theorem. So that's honestly just good math strategy. Do the way that's going to be the simplest and most effective and efficient. We're doing the same thing here. We're going to find x, y, and z. So we want to set up our small, medium, and large triangles with the parts that we know. So we have 9, 12, and then x and y. We have, for the smallest one, x, z, and 9. And for the medium one, we have z, y, and 12. For this largest triangle, I can easily find the whole hypotenuse, so I'm going to go ahead and do that real fast by using the Pythagorean theorem again. So I have 9 squared plus 12 squared is equal to, I'm just going to say c squared. So that is 81 plus 144 equals c squared. 81 plus 144 is equal to 225. So 225 is equal to c squared. Square root both sides, and 15 is equal to c. This is not something that it asked me to do, but I'm going to use the fact that this is 15 to now set up proportions. To figure out what y is, I can easily say, oh, hypotenuse over hypotenuse corresponds with bottom over bottom. So that's what I'm going to do to figure out what y is. So I'm going to say 12 over 15 is equal to y over 12. So cross multiply. I have 15y is equal to 144. Divide by 15 on both sides. And we're going to get 9.6. So I'm going to write that in my triangle. I can do that again for the z. So instead of using the hypotenuse as an unknown, I can use the z. So I can say this z corresponds with this 9, and I can still say the 12 corresponds with the 15. So let's do that. Here, we're going to say z over 9 is equal to 12 over 15. Cross multiply, I have 15z, 15z is equal to 108, because 9 times 12. Divide by 15 on both sides. And now I get z is equal to 7.2. I'm now nearly done. I just need to figure out one more value. Well, I can also use the smallest triangle to figure out the x. This x is still corresponding with the 9 down here. So I can say x over 9 is equal to 9 over 15. So let's do that to calculate my final variable. So I have x over 9 is equal to 9 over 15. That's 81 is equal to 15x. Divide by 15 on both sides. And that gets me x is equal to 5.4. So I had to use the Pythagorean theorem kind of as a middle step, and then I used cross multiplication for all three of my variables. Once again, it's kind of up to you to determine which way is going to be easiest for you to get there. Alrighty, for my final example, it says, to estimate the height of a Douglas fir, Dan positions himself so that his lines of sight to the top and bottom of the tree form a 90-degree angle. His eyes are about 1.6 meters above the ground, and he is standing 7.8 meters from the tree. What is the height of the tree to the nearest meter? What I would like you to know is that there is another kind of shortcut to this type of problem, and it is this. The altitude is the geometric mean. The altitude is the geometric mean. So that means this altitude right here is going to be in this position in a proportion. What is it a geometric mean to? It is the geometric mean to this half and this half. So that's what I'm going to do. I am going to set up a proportion to solve for that. I am trying to figure out this height right here. So I'm going to say x over 7.8 is equal to 7.8 over 1.6. Why did I do it that way? Once again, the reason I did that is because, and this is just a little property that I didn't put in the notes, but it's a property that I'm just letting you know it. The altitude of the largest triangle is a geometric mean to the two halves, or the two parts, I should say, of the hypotenuse. Well, the geometric mean is in this location in a proportion. So now I want you to start solving. We have 1.6x is equal to 60.84. divide by 1.6 on both sides, and we get x is equal to 30, let me look here, 60.84 divided by 1.6 is equal to 38.025. So from here to here is 38.025. The question is, what is the height of the tree to the nearest meter? So what we're going to need to do is take this number plus the 1.6 to get the tree's final height. So I'm going to have 38.025 plus 1.6. And when I do that, I get 39.625. It then says round to the nearest meter, so I'm going to say 40 meters for my final answer. Just to reiterate, the highlight of today's lesson is going to be these style of examples where you can take that triangle and separate it into 3 similar ones. And remember to keep your proportions similar and to match up corresponding parts. I hope you have a great night, and I'll see you soon.